Good evening and welcome to Everything Matters, Tales from the Periodic Table. Tonight we're going to be doing titanium. My name is Ron Hipschman and I'm hosting the series Everything Matters. We will be having, our program is split into two parts. I'm going to give the first part tonight, and I'm going to talk a little bit about the chemistry and the history and some of the applications that titanium is used for. And in the second part, I'm going to be followed by Stuart Goodman, Dr. Stuart Goodman, and I'm just going to tell you, I'm going to read the vita here. Stuart is an academic orthopedic surgeon at Stanford University who partakes in clinical care, education, research, and administration. Dr. Goodman's subspecialty interest is in arthritis surgery, including primary and revision joint replacement of the lower extremity. His research interests include orthopedic biomaterials, biocompatibility, and tissue engineering of musculoskeletal tissues. That's why I had to read it. And that's going to be a really interesting talk. So when I finish my talk, we're just going to break really quickly. We're going to bring up his slides and introduce Dr. Goodman. And so don't go away after I'm done. I'm just going to spend about 20 minutes talking a little bit about titanium. So titanium, we look at our periodic table. Titanium is element number 22. You can see that they're sort of on the upper left of the screen over there. I have a hard time seeing it myself. It's right about there. And, well, let's bring it up. There's titanium. It's element number 22, which means it has 22 protons in its nucleus. It has a variable number of neutrons depending on what isotope we're going to be talking about. We'll talk about isotopes when we get there. But the 22 protons in the nucleus says, I am titanium, because that means it also has 22 electrons surrounding the nucleus. And those electrons are responsible for all the chemistry that we're going to talk about. Now, it was originally discovered by this fellow, William Gregor, and in Cornwall, Great Britain, in 1791. And he actually didn't see the metal itself. He was looking at minerals. Specifically, he was looking at a mineral called ilmenite, and he found a strange substance in there that he couldn't quite explain, and he was therefore the first one to see this substance. It was really titanium dioxide, not titanium itself, but we also find titanium dioxide in rutile, which is one of the main sources of titanium. And these deposits occur really all over the world: Australia, Canada, China, India, Mozambique, New Zealand, Norway, the Ukraine, South Africa. So it occurs in a lot of different places. This fellow, Martin Klaproth, he was actually independently discovered titanium dioxide as well. He did this in 1795, and he, however, decided that when he was able to separate things out, decided that this dioxide, this titanium dioxide, did contain something new, a new element. And he gave that new element a name. He named it after the Titans, hence titanium. But he, again, never saw the actual physical metal. This fellow, Matthew Hunter, was the first one to actually synthesize and purify the actual metal, and that to some purity, about 99.9% pure, and he did that in 1910. So we actually didn't see the metal titanium until 1910. That's pretty late. He did that at Rensselaer Polytechnic Institute, and he heated titanium tetrachloride, which, by the way, is a really interesting liquid. If you put it out, it just smokes. They use it in movies a lot as a smoke generator. And he heated that with sodium to a very high temperature under great pressure, and he was able to actually produce titanium at a fairly high purity. So that's what titanium metal kind of looks like. We have some samples of titanium for you to come up and look at after. It's has very useful properties, titanium. It has amazing corrosion resistance, and it has a very high strength to density ratio. So it's a very strong metal, as strong as steel, but it has a much lower density than steel, so it's much lighter than steel. And that makes it, and it also because of its corrosion resistance, makes it really, really useful. It's produced in a good quantity. About 186,000 tons of it are made every year. And it's produced, again, all over the world. But 2/3 of the titanium produced are not produced for the metal. They're produced for that titanium dioxide, and we'll get to that. So titanium is not a very common element in the universe. It's about the 20th most abundant element in the universe. It only makes up like 0.0003% of the universe by mass. But we move in now. You would suspect that the sun would have about the same amount, and it does. It's about the 21st most abundant element in the sun. And if we look at meteorites, it's the 29th most abundant element in meteorites. But when we get to the crust of the Earth, we get up quite high. It's actually the 9th most abundant element in the crust of the Earth. It makes up about 0.2% of the Earth's crust. That's quite high. It's actually the 7th most abundant metal in the Earth's crust. So it's actually quite common, but it doesn't occur as metal. It's always in a chemical form, a different chemical form. Mostly the titanium dioxide. We move to the oceans. It goes way down in abundance. It's only the 32nd most abundant element in the oceans. And in us, it doesn't occur. It is not essential to biology. There's no titanium in the human body unless it's implanted, and we'll get there. Titanium is made only in very, very large exploding supernova. So if it's a young star that's made out of new hydrogen gas, you have no titanium. Our sun has titanium, and the only reason it does have titanium is because it's made from the gas and debris of older stars that have exploded. So that's why we have titanium. Now, I mentioned isotopes. What's an isotope? An isotope is something that has all of these things are titanium. They all have the same number of protons, 22, but they have different numbers of neutrons in the nucleus. So there's heavier titanium and lighter titanium. And that number you see up at the upper left of each TI is the total number of particles in the nucleus, protons plus neutrons. Now, not all of those isotopes are stable, not radioactive. These are the non-radioactive ones. There's only 5 of them. So titanium 46, 47, 48, 49, and 50 are the only stable isotopes of titanium. All the others are radioactive. We'll get to those in a moment. And these make up in various abundances on the Earth. Well, you can see that actually titanium 48 is the most abundant, making up about 3/4 of all the titanium that we have, with a few percent here and there of the other isotopes. Now, if we move on to that radioactive stuff, they all decay, and some of them decay faster than others. And the rapidity at which things decay we call the half-life. It's the amount of time it takes for half of the atoms in any given sample to decay. Doesn't make any difference how big the sample is for half of the atoms. So the longest lived isotope of titanium is titanium 44, and that has a half-life of 63 years. That's not really long. Like uranium 238 has a half-life of 4.5 billion years, which is why we still have a lot of uranium around. But if only 63 years is the half-life of titanium, there's basically no titanium 44 because it's all decayed away into other things. The next longest half-life is titanium 45, 184 minutes, and titanium 51, 5 minutes, and titanium 52, 1.7 minutes, and all those other isotopes you saw on that table, less than 33 seconds. And some of them last milliseconds, half-life of milliseconds. So there's lots of forms of titanium. Only 5 of the isotopes are stable. All the others are radioactive. Titanium, I mentioned density. Titanium has a fairly low density of about 4.5 grams per cubic centimeter. Remember, water is 1 gram per cubic centimeter. And I labeled a few down here just for comparison. So iron, steel, has a density of about 7.8 grams per cubic centimeter. So titanium is less dense than steel, but you'll notice that aluminum is 2.7 grams per cubic centimeter, so it's sort of midway between steel and aluminum density-wise. Now I have down here, and I want you to come on up after. Some of you who have been here before probably have done this, but the newbies, I have a bunch of blocks of different materials of different densities. They're not quite all the same size yet. We'll work on that. But down here you see we have, well, a range of densities. So we have tungsten, and we have lead, and we have copper, and iron, and titanium now, and aluminum, and at the bottom, magnesium. And there's titanium. So it's kind of in the middle-ish range there. It's a nice, we'll try to fill in some more of those too if we get the chance. The problem is they have to not cost like gold or something like that. I calculated it out. A gold block that size would be about $140,000, and that's not in my budget, is it? No, it's not in my budget. But titanium is relatively cheap. Titanium is only about $40 a pound for fairly pure titanium. The titanium I have down here is, well, one of the blocks is the small block is fairly pure. The bigger block is 90%, which is not super pure, but it's the one that's used for machining and making engine parts out of. The atom of titanium is fairly large, much bigger than hydrogen, because there's a lot more things in there too. And it has some free electrons on the outside, which tends to puff things up. It has an interesting spectrum. It has a lot of lines in its spectrum, all those bright lines in its spectrum. Actually, you can see a lot of those in the sun. And that tells you that the sun has titanium in it. You look at the sun's spectrum and you can tell what elements are inside the sun. You don't have to go to the sun and take a teacup full of it. Don't go to the sun. Or go at night. And you don't have to go there. You can look at the spectrum and tell what's in the atmosphere of the sun. And so we know that the sun has a fair amount of titanium in it because we see some of those colors in the sunlight. So looking at some of the applications, one of the major applications of titanium is titanium dioxide. About 95% of all the titanium ore is destined to be refined into this white powder, titanium dioxide. It's intensely white and very, very opaque. It's used in, well, you probably have seen stuff like this, artist paint. This is titanium white. There's a reason it's called titanium white. It's titanium white because it has titanium dioxide in it. And most white paints are white because of titanium dioxide. It just is a great pigment. It's also used in toothpaste and plastics. Anytime you find a white plastic, it's always the pigment in white plastic. And it's very inert to titanium dioxide. Titanium dioxide, remember that mineral we talked about first, rutile. It comes in very needle-like crystals, and if you embed these needle-like crystals along crystalline lines in something like aluminum oxide, these little crystals will bend the light and form the star in the star sapphire. Now, the sapphire itself is aluminum oxide, but the titanium dioxide crystals give it this little starburst inside the star sapphire. Beautiful, beautiful gemstones. If you combine titanium with nitrogen, you get a very, very hard substance called titanium nitride. And they use titanium nitride as a coating on drill bits, on razor blades. It's a very, very hard substance. It's about the same hardness as ruby, which is, anyone remember the Mohs scale of hardness? Diamond is 10 and talc is 1. Well, it has a hardness of 9, so just below diamond. So where else is it used? We're going to get into this more later, but it's used in dental implants. Anyone have a dental implant here? There's one person back there. So if you've lost a tooth, they'll screw this thing into your jawbone, and then this post is sticking up here, and they'll attach a fake tooth to the top of that. Good as new. Now, the fellow who did this book here, which is one of my favorite books about the elements, Theodore Gray, which I use a lot of his pictures, but Theodore Gray did this book, and in his book he has lots of pictures of places where these elements are used, like this dental implant. And under titanium, Theodore Gray has a picture of Theodore Gray because he has dental implants, and so he felt that he should include himself among the titanium samples. So I kind of like that. There are uses for titanium that frankly I don't understand, like making a titanium hammer. A hammer is meant to be heavy, to pound nails in. You want a hammer to have a lot of inertia. Making a hammerhead out of titanium makes no sense to me whatsoever because it doesn't have the inertia of an iron or steel hammerhead, but I guess you can charge more money for it. That's true. When you carry it around, it would be easier to carry around. That's right. That's a good point. Remember, it has a high strength to weight ratio, which means that its use in bicycle frames might be a good use for it, and you can buy bicycle frames that are made of titanium. They're expensive. You know, you're going to pay a few $1,000s for a titanium bicycle frame. One of my favorite uses, given my predilection for computers, was the titanium power book, which I still have. I couldn't give it up. I still have my titanium power book right here. And in this case, Mr. Jobs decided that it would be really cool to make the entire case out of titanium sheet metal, very, very, very strong, which means you can make this display cover like really thin. It's because it's fairly rigid. Of course, Steve was not the first thing. Steve liked elements too. You could tell this because when at his previous company, Next, he made his Next computer out of magnesium. Much more exciting, actually. Do not dispose of your Next computer in a fire. Of course, you can use titanium, since it's light and strong. Camp gear is a real popular use for it. If you have a lot of money to spend, you can buy, it's not super expensive, you can buy titanium camping gear. And I was just, this is what I have my stuff here. I have my titanium spork. You got to have a titanium spork. It's very important. Why, if you're trying to lighten your load, why carry a fork and a spoon, right? And I've been lusting after my a pair of titanium chopsticks. Now I've got it. Thanks to Everything Matters, I now have a set of titanium chopsticks. But you can get everything: thermoses and pots and pans and knife and fork sets and things like that. Now we have here at the Exploratorium, there's a really cool application of titanium. This building is heated. We have by a radiant floor. The floor that you're sitting on right now has 45 miles of plastic pipes running in it. And if you run hot water in the pipes, it heats the building up. If you run cold water in the pipes, it chills it down. Where do we get the hot and cold water? Well, we get it from the bay. The salt water underneath your feet here. We draw it up, and we send it out to a room, which is actually just behind you here, a heat pump room, and we make from the bay water, it's just the right temperature, we can make hot and cold water. It's a heat pump, produces both. And if we want to make the building hotter, we pass the heat, but we don't pass the salt water through the pipes in the floor. We only want to pass fresh water through pipes in the floor. To do that, we have to somehow move the heat from the salt water into the fresh water. That's done with a heat exchanger. This is the heat exchanger that's sitting in a different room. You can see it if you go all the way to the back here. We have our pump room with a big window in it. And here, these are a bunch of titanium plates that are right next to each other. Actually, here's the model of that heat exchanger. So this is a bunch of titanium plates, and you put hot salt water here, and fresh water here, and salt water here, and fresh water here, and salt water here, and so on. It's opposite. It's alternating salt and fresh water, and the heat is transferred from the salt water into the fresh water, or if you're trying to heat the building, or the heat is taken out of the water if you're trying to cool the building. And if you look, this is what those plates look like. So you have salt water, fresh water, salt water, fresh water, salt water, fresh water, salt water, fresh water, and so on. Even though titanium is not a very good conductor of heat, if you have enough of them, It's much better because we're dealing with salt water here. You don't want to corrode this thing. And so even though it's not a very good conductor of heat, the corrosion resistance of titanium really helps us here. Where else is titanium used? Well, we may have heard that the Russians are famously use titanium for the skins of their submarines. This is an Alpha class submarine right here with a titanium hull. It also has it's a nuclear-powered submarine, and it's one of the fastest and deepest diving operational submarines ever built. It's pretty big. It's 390 feet long, so it's about the width of our pier here, so it would fit across the end of our pier. It's big. But there's only 32 officers running this thing, so it's pretty efficient, too. We have built aircraft. This is one of the first aircraft, the North American F-100 Super Sabre, and this is a supersonic jet fighter that had engine parts, one of the first aircraft with engine parts that were built out of titanium. But we built a much more evil-looking aircraft out of titanium. The SR-71 was built out of, the Blackbird was built out of titanium. They didn't build many of these things. They were only built 32 of these. If you want to see one of these things, by the way, the California Science Center in LA has one of these things outside. It's an amazingly, it's kind of smaller than it looks here. This was not a really good aircraft. It was very fast, but it leaked like a sieve. They had a hard time keeping the fuel tanks sealed. As a matter of fact, you can even see the fuel leaking out here on the wings. But it was a Mach 3, 3 times the speed of sound aircraft, which meant if you fired an anti-aircraft missile at it, no problem. It could outrun anything. So you just had to fly. So there's one more application I want to talk about, which is really kind of cool. We're going to do a little demo for you right here. And that's with a special wire, metal, that uses titanium called Nitinol. Nitinol, you can tell it has about equal amounts of nickel, the Ni, and titanium, Ti. And the NOL actually stands for the place where it was actually invented, the Naval Ordnance Laboratory. So Nitinol is a very interesting metal. I have some wire here. So this, if I can pick it up, there we go. Nitinol is it's a wire that when it's cooler than a certain point, when you bend it, it stays bent. But it remembers what it was originally. I'm going to kind of coil this around my fingers here into a coil. So there we have a little coil. And I'm going to put some hot water into this dish over here. Because when we get it above a certain temperature, in this case 40 degrees centigrade, sorry, Celsius, I'm just going to remember that it was a straight wire. Here we go. Let's dip that last end in there. Ready? It remembered it was a straight wire. Should I do it again? And, well, it really does it violently. Here we go, one more time. Boink. So it actually is a memory metal. It becomes very stiff above that critical temperature of 40 degrees C. You can build some very interesting devices out of this, and Maker Faire is this weekend, by the way. You'll probably find some projects at Maker Faire that are made out of Nitinol wire. Amazon, if you're looking for it. With that, I'm just going to go past this since we did it live. So let me tell you that next month, our last Everything Matters Tales from the Periodic Table for the season will be vanadium. So that will be on June 15th at 8 p.m. I also do another set of talks called Full Spectrum Science. That's still coming up this month, the 4th Thursday evening and the 4th Sunday afternoon. So that's coming up on May 25th and May 28th. And this month, we're going to talk about making sound. So I want to invite you back for that. And thank you. We're going to have Dr. Goodman come up now, and we'll continue on with the second part of our talk here. Thank you.
Well, thank you very much. I'd like to thank Andrew and Ron and the rest of the crew here for the invitation, and thank you for coming. I'm going to give sort of a medical spin on this because I am an orthopedic surgeon who does some research also, and I get to use all these fun materials every day. So let's just go right into it. So the demographics of the population are changing. We can see that my grandmother didn't do this. I don't know about yours. But when you look at activities of people who we used to consider our elderly, there really are no limits. This lady's over 90, and the rest you can read. We're all more active than our elderly grandparents. Now, what does this do for our joints? Well, if we look at this table here, we can see just standing about 1 times body weight because of our muscle forces. And if you go up this table to the top, just ascending and descending stairs, 300% of our body weight, 3 times our body weight, because it's not just our weight. The muscles create load. They create force. And if you're going to invent some sort of prosthesis, you have to account for all these forces. Now, this is what Leonardo da Vinci visualized when he thought about humans. But humans aren't like that now. You can see we've got knee replacements and hip replacements and pacemakers and artificial this and that. And this is the beauty of modern technology. And that's why we all have to be very cognizant about materials. Now, I thought I'd tell you a little bit about osteoarthritis. So it's a disease that affects about 1 in 3 Americans, especially the older you get, the more chance you're going to get osteoarthritis. And it's a wear and tear disease of the large joints here, the hips and the knees and the shoulders and the fingers. And this is a knee that has very bad arthritis. You can see, you can't really see the joint spaces. In fact, there are no spaces in certain areas. And it affects the whole knee, the muscles, the ligaments, the tendons, the cartilage degrades, and it's painful, and it's difficult to be functional with a knee like that. So one of the things I do a lot of every week is I do total joint replacement. Now, these are artificial materials, some of which are titanium, which I'll tell you about, and they allow the reconstitution of surfaces that mimic what joints normally do. And they're pretty good. So here's knee replacement, a partial knee, a shoulder, total hip replacement, etc. Now, actually, total joint replacement is the most cost-effective operation in all of surgery. It's time-proven, decreases pain, improves function, improves mobility, and improves psychological well-being. This is a picture and the book by Sir John Charnley. Sir John Charnley basically invented and put total hip replacement on the map. A lot of this work was done in his garage, believe it or not, in the early 1950s and 60s. And we can see him, he's no longer alive, but this is one of the first total hip replacements. And you can see that there's a femoral component in the femur, there's a socket, and it's cemented into place with something called polymethacrylate, which is like plexiglass. You mix it up, it's like dough, and it hardens. The trouble was, as time went on, people modified Sir John Charnley's principles. His original total hip replacement here was made out of stainless steel. And this is polyethylene on the other side. But notice the small head and thick plastic was changed over the years by many different inventors to the detriment of the operation. And it has to do with biomaterials, biomechanics, and how you can anchor this within bone. So what happened? This is a total hip replacement. You can see, this is one that I revised many years ago, but you can see here's the stem. This is cobalt chrome. I'll talk about this later on. This is the bone cement, but notice the bone cement has broken down And we can see big holes everywhere. It's sort of like going to the dentist where he or she looks at the x-rays and sees these holes around your fillings, and they say, uh-oh, you know, you need a root canal and this or that, and this is what happens or happened with total hip replacements anchored by cement with older cement technique. We're better at it now. Now, not only was cement a problem at one point, but also the bearing surfaces were rather older. So here's a cementless hip replacement, which I'll tell you about in 1 minute. But notice the ball in a metal socket with plastic, but notice the ball is not central because the plastic is worn. And cells don't like particles which are generated by wear, and so the cells can't digest these particles, so it activates them. They spew out enzymes that makes holes in the bone, and that's called osteolysis. And that's been my research for 30 years, studying how this happens, why it happens, why joints succeed, what are the best materials, and what are the cells doing. We'll talk a bit about that later. So instead of a metal on plastic articulation or bearing surface, people have experimented with metal on metal, I'll tell you a bit about that, ceramic on ceramic, and made plastic better. And what I use today is generally a metal or a ceramic head. This is called highly cross-linked polyethylene. It's plastic that's been cross-linked so that it's more durable. This is a metal on metal hip replacement right here. It's hardly done anymore. This is a metal on metal resurfacing arthroplasty. Now, why don't we do a metal on metal hip? Because if you think about it, these hard bearings have to be perfect. Plastic can wear a bit, there's a bit give. But a metal on metal implant, when it wears, if something's not perfect, if it deforms or there's sort of a third body, like a breakdown product in that meeting, then particles get generated. And I study particles. I study cells and the reaction to particles. And metal particles made out of cobalt chrome are bad. And they do things to genes, they kill cells, and you can get really bad things, such as big sort of tumor-like things that happen in the soft tissues. And you rarely see metal on metal joint replacements now. They've almost been abandoned except for a very small situation. And sometimes we see this metal breakdown with modularity. So we have modular implants, so we can change the size, the ball size. They come in different parts and different sizes. But this can lead to degradation. This can lead to the breakdown of the surfaces, like Ron has told you about, due to corrosion. And that's where titanium comes into, and I'll talk about that in a minute. Okay, so we're now into the 1980s, and or 1990s too. I've been at Stanford since 1985, and we're seeing more and more of these hip replacements with cement that are loose, and look at the bone destruction here. So this is the bone cortex here. You follow it up, and it starts to disappear. And the patient has pain because this is a loose implant, and I've got to revise it. And these were hard revisions because there's not a lot to put back into the bone. So we had to use bone from cadavers and wire it on and do all sorts of things. So around this time in Sweden, this researcher in Gothenburg, named Brånemark, I spent some time in Sweden and did some research with this group. He was doing some work in rabbits, looking at how bone heals. And he put these titanium chambers in the rabbit tibia here, connected a microscope up, and day after day after day for months and months and months, he would look at how bone vascularizes, how blood vessels grow in, and how bone heals. And when the experiment was over, these are very expensive chambers, he said, well, let's get the chamber out and put it in another rabbit so we can increase our number sizes and have a good series, because no one wants to report only one rabbit or one specimen. He couldn't get the chambers out. And he said, something's going on here. And these were commercially pure titanium chambers. And that's how he realized that bone loves titanium alloy. He couldn't get these chambers out. And he coined the term osseointegration. Osseo is bone. Integration means healing of something right next to the implant of bone. And Ron's already told you about the dental implants. This all comes from Sweden. Okay, so the first dental implants were placed in Sweden, and they can be in the mandible or the maxilla. If you lose a tooth, they put a post in the bone, and it osseointegrates, and then weeks or months later, they pop an artificial tooth on it. And I don't have any yet, but my friends who have many tell me that it works great. They can eat apples and chew gum and do just about anything. And it's really revolutionized all of dentistry. And this is what osseointegration looks like. So here's a screw that was screwed into the bone. This is actually bone tissue that has an intimate contact. It anchors it. So osseointegration is a real great thing. Now, osseointegration can go the wrong way. So it works if you have a material, that's great. If you have a bed, that's good. So you don't want poor bone stock or infection or irradiation. The host has to have the right constituency. The implant has to have the right characteristics, surface coating, etc., etc. And what does this have to do with total joint replacement? Well, you remember the cemented implant I told you about. So a number of people who I actually worked with a long time ago, I mean, I'm not like 110, but this is actually more recent, 60s, 70s, 80s. They thought, why can't we get rid of bone cement overall? Because bone cement is one of the weak links in a total joint replacement. It's great because it's like silly putty that can anchor and then harden, but the technique is difficult, even though our total knees are done almost exclusively with bone cement. That's why the residency is so long. You have to learn how to use it. And so several people in Toronto and Chicago and around the world thought, why can't we coat a prosthesis with beads and machine the bone so that we jam this thing in and it's got stability at time 0, and then bone can integrate into the prosthesis and we don't need bone cement. And that's called porous coating. These little bumps have pores between them and the bone can grow in. So what does this have to do with osseointegration? I'm getting there. So you heard all about this. I'm not going to repeat all of this here, but the interesting part is without titanium, we would still be using cobalt chrome implants. Cobalt chrome implants are great. We use them all the time. But titanium is lighter. I think I have a slide on this. You know where it is on the periodic table, right here. And you know it's strong, it's low density, high strength, and it's resistant to corrosion. Think about an implant being in your body, and the implant is exposed to physiologic tissues that create an environment that you want to break down tissue. And titanium is really good because it oxidizes. It oxidizes immediately, and that makes it resistant to corrosion. And you've heard from Ron all of these applications. Highly reactive with oxygen. It passivates. It gets this nice oxygen layer. The only thing about titanium alloys is that they're a little notch sensitive. So as opposed to cobalt chrome, if you nick and put a notch in titanium or titanium alloy, it's much more sensitive to breaking than, let's say, stainless steel or cobalt chrome alloy. Okay, the other thing about titanium alloy, and I have a graph on this later on, there's no test on this, by the way, at the end, so you don't have to memorize it. Bone has a certain stiffness. What you want to try and get is an implant that has a stiffness as close to bone as possible, so the bone doesn't remodel in a bad way. Now, if you look at this table here, stainless steel and cobalt chrome are very, very stiff. What you want to try and get, bone is like 10 to 50 gigapascals. Stainless steel and cobalt chrome are much, much, much stiffer. But look at this, titanium alloys are half of that. So we're getting closer to the stiffness of bone. So the bone can say, oh, gee, I have something in me that's more like me, and so it won't remodel as adversely as it would around something that's more stiff. Now, in orthopedics, we use mostly what's called titanium 6 aluminum for vanadium. It's good you're taking vanadium next month. So most of this, about 90% of the implant is titanium, but about 5 to 10% are aluminum or vanadium. And they add to the ability to resist corrosion and a few other properties too. So I was telling you about this chart. So if you think of cobalt chrome alloy here being real stiff and bone being around here, look at how much closer titanium alloy is. And I'll tell you about tantalum. We're using tantalum now to coat some of our titanium alloys so that when you have the implant and then the bone, you can put something between it, tantalum, that's a little more bone-like. It has less stiffness, so the energy dissipates through that different interface. Okay, I want to talk a bit about the biological reaction to implants, because this is where I do a lot of work here. And when you put anything in the body, it doesn't matter if it's in the heart or the brain or the kidney, there's a lot of things that you have to think about how your body is going to react to that implant. You have your host characteristics, your genetics. Where are you going to put it? What's the mechanical environment? What are the characteristics of the whole implant? And there's other factors. Is there infection? We hate infection. An implant that's infected generally has to come out. And when you do any surgery, you evoke an immune response. It's a natural way that we respond to injury. When you put an implant in the body, whether it be a catheter or a hip replacement, you not only have the surgical procedure and inflammation, you also have the inflammatory reaction to the implant that hopefully will settle down and allow that implant to be incorporated into your own body. So here's a patient of mine who's got, here's a normal hip. You see, round ball, good space. Not a round ball, no space, cysts. And this patient's in chronic pain, activities of daily living severely encumbered. This is what a cementless hip replacement is. Here's the stem that's jammed in here, titanium alloy, surface made out of titanium with wires on it so the bone can grow in. Here's the cobalt chrome head and plastic, the special plastics in here. Here's a cup, titanium alloy, and some screws to anchor it down. And these patients can do just about anything. We don't like them doing high-impact sports, but walking, swimming, bicycling, cross-trainers, all that stuff's fine. And they're very active. Here's a patient who you can see has a congenital dislocation of the hip. Here's a normal hip in the right place. Notice the socket never grew. It's like a cliff. And the hip's dislocated. It's way up high. So you can't just yank this down because all the nerves and the arteries are shortened. So you have to do a very specialized operation and measure all things out and use some wires to put some of the muscles and tendons back. But here is a press-fit titanium alloy stem with a cup and head, plastic, some screws, osseointegrated, leg lengths look great, changes people's lives. And that's why I like to do it. These are hard operations, but they're very good. Now, what can go wrong? Okay, what happens when Merv's manure hits Sam's fan? You're recording this, so I can't. Okay, things can go wrong. Okay, so here is an implant. It's cobalt chrome, long one, thin. You see what happened, broke. Okay, and I revised this as a titanium alloy here because the bone was so bad. I took a strut of bone from the bone bank and I wired it on and bone grafted it, and this incorporates into the patient's own bone. Successful, happy operation. This is an example of a retrieved implant I had. So you've got the stem, you've got the ball, you've got the plastic, which I don't show because the ball eroded right through the plastic. Patient didn't come in. This is not my patient. It came to me, or the patient came to. But it's nice to see this patient earlier before the ball goes through the plastic. And look, it went right through the cup. And when I revised this patient, even though the stem wasn't loose, look what I found. A little notch right there. So this little area right here, as the ball went through, and went through here, it caught on this area. I had to take the stem out. And so this added an extra 2 hours to the whole operation. Instead of being 2 hours, it was like 4 hours. And this is very rare, but this is why we can't leave a titanium alloy stem that's notched in there. Things can happen. This is a poorly designed titanium alloy stem. And you can see it's a modular neck. This is one piece, this is another piece, and look what happened. So I'm very cognizant of STEM design, I was a consultant for the FDA looking at all these new things for sometimes, and it's very, very strict. We have a whole bunch of people that go through all the data, and this should never happen. Titanium alloy osseointegrates, and we now understand all the cells that have to come in and make bone. But if things don't go right, you can get inflammation, and inflammation doesn't lead to bone growing in. So we're experimenting with a lot of different models and animals. We retrieve tissue and all the rest. And one of the models is one of the models that came from Sweden. This is that chamber. It's a modification of it that is placed in the rabbit tibia. It osseointegrates, and we can harvest what grows in through this hole here every 3 weeks. And it's commercially pure titanium, and we can take it apart through a small incision in the tibia skin and harvest it every 3 weeks. If we do that after 3 weeks in this chamber, we see bone grows in longitudinally. But if we put in particles of cement or cobalt chrome, you see much less bone. But look at this. This is titanium alloy particles. Same concentration. Look at all the bone. Okay? So titanium's a bone-loving material. The tissues like it. And this is one thing that we wrote up in some of the journals. Now we're into more sophisticated models. This is a mouse model, which we have where we can put particles in here, and we can pump them through a hollow titanium rod into the mouse femur, trying to figure out how we can make implants better, how we can understand the biology of how osseointegration occurs and how particles generate a tissue response. And what we can do is something called micro CT scans. We can look at all the holes in bone and say which is a better material and how much it breaks down. We can quantitate it, and we can help invent new materials and new models to test things that might go into people in 10 or 15 or even 20 years. And we can also trace what cells do. So in some situations, we actually inject inflammatory cells away from this area, and these cells will migrate to the area where the particles occur. So you're thinking, what the heck does all this mean? Where are we going? This says, these two wolves are saying, my question is, are we making an impact as they howl at the moon? Sometimes I wonder this in science. Are we making an impact? Well, here's where I think we might be making an impact. By understanding how these materials interact with the body, with different cells, whether it's hypersensitivity or osseointegration, we can better design materials, and we can understand how the byproducts of these materials lead to a good or a bad clinical result. And that's the whole focus of the research that our group does at Stanford in this area. And we actually have invented and shown that there are certain things that we can do to implants. For example, we can infuse certain, we can coat implants so that we attract the cells to come to help it integrate. We can actually block the bad cells from coming. And if the bad cells do come, we can change them from bad guys to good guys by infusing something called, it's a small molecule called interleukin-4. And we can understand all this talk between bone cells and blood cells and how we can modulate this whole reaction. Certain drugs have revolutionized the treatment of rheumatoid arthritis. Well, we hope to do the same for implants so that when you get it, then people won't have to see me to have a redo. But 50% of what I do are doing implants from all over that have failed. I'd rather not do those at all. And in fact, I'd rather not do total joint replacements at all. We are also working on tissue engineering to engineer cartilage and bone so we won't even have to do the original joint replacement. But still, we're not even close. But we are closer and closer to getting better materials and understanding these reactions better. We have new materials, as I was saying, like tantalum, which are more close to bone. Now, tantalum doesn't have the strength of titanium, so we can only coat with tantalum. But if bone cells will come in and integrate that implant better, then that's a good thing. And this is where tantalum is, not too far from titanium. So it'll be, what, a couple of years, Ron? But I think you'll get there, right? Yeah, maybe a few years. And there's good work in humans and in animals showing that tantalum works not only probably as good, but probably in some situations better than titanium alloy. And now we have implants which are made out of titanium alloy, but coated with tantalum so that bone can grow in, and we can make these tantalum surfaces very bone-like with pores in them, just like cancellous bone. And here are some examples. We can actually even do that with titanium. So here's a porous augment for a hip replacement or a knee replacement to replace lost bone. And we can also try and invent even new materials, not only titanium, but alloy it with things which are stronger, more resistant to corrosion, and somehow get things to last even longer. We can also coat implants, and here's a paper that I did with the Hipschman group, who are biomaterials experts at Stanford, where we're coating implants to get them to integrate better and to prevent infection. So where does this leave you all? Well, I think, to summarize, I think what Ron and I have been saying is, you can read the periodic table and you can memorize it, but when you see all the research and all the exciting, innovative things that one element has done, and where the research and the applications are going, then it becomes very, very exciting. We hope to have implants that last longer, not only in hips and knees, but in the mouth, all over the body, that are more corrosion resistant and more functional, and hopefully will last a lifetime. Now, this is our lab group, which I have to mention because they do a lot of the work and they're from all around the world. And this is our funding, and I'm very grateful to NIH. Please keep the money coming from NIH because it really helps us all, and it's responsible for a lot of the interesting things that we've talked about today. Thank you very much.
Thank you, Dr. Goodman. I want to also mention that if you really, really like, it's getting a little late in the year, but we do have a periodic Everything Matters calendar, small and big. And this book, the Theo Gray book, is also in our store. Please come on up and check out the densities here. And also, we had one of our regulars here brought in a titanium femoral rod. Thank you for that. And the screw that holds it in. So you might want to just take a look. This is an actual thing that was actually in somebody. Maybe you'll come on up and talk about it. But again, check out the titanium. Come back next month for vanadium and for full spectrum science. Thank you all for coming.